Welcome to the video. Today we are exploring how a convolutional neural network or CNN can recognize handwritten digits using the famous MNIST dataset. This project is one of the best ways to understand the basics of deep learning. Throughout this presentation, I'll walk you through the dataset, the architecture, the implementation in PyTorch, the training results, and finally the model's performance. So let's get started. Before we move to the technical part, let's understand why CNNs are perfectly suited for this task. CNNs are designed for image data. They automatically learn edges, curves, strokes, and shapes, which is exactly what we need to understand handwritten digits. They are used in real systems like number plate recognition, bank check reading, postal sorting, and mobile OCR apps. The MNIST dataset is the best place to begin learning CNNs. It contains thousands of handwritten digits from different people, making it ideal for training models to recognize patterns. It's simple, clean, and widely used as a benchmark to test new models. MNIST contains a total of 70,000 images, 60,000 for training and 10,000 for testing. Each image is 28 by 28 pixels and in grayscale, which is perfect for neural networks because the input size is small and easy to process. Even though the images are tiny, they come in a variety of handwriting styles: thick, thin, slanted, curved, sharp, messy, neat, everything. This makes the dataset simple but still challenging enough to teach a model how to generalize. Here's a breakdown of CNN architecture used in our project. We start with a convolution layer which scans the image and extracts low-level features like edges, corners, and shapes. Next is ReLU activation, which introduces non-linearity. This helps the model learn more complex patterns instead of just straight lines or simple shapes. Then comes max pooling, which reduces the size of the feature maps. This makes the computation faster and also helps avoid overfitting. After that, we use a flattened layer which converts the extracted feature maps into a one-dimensional vector. Finally, we pass this vector through fully connected layers. These layers learn high-level patterns and relationships, basically deciding which digit the features match. The last layer predicts a value from 0 to 9. Despite being simple, this architecture can reach nearly 99% accuracy. To build this model, we used Python and PyTorch. We started by importing all necessary libraries for neural networks, data handling, and visualization. Then we downloaded the MNIST dataset and applied basic pre-processing like converting images into tensors and normalizing them. After that, we defined the CNN module using PyTorch's nn.module class. We set up the loss function, cross entropy loss, which is perfect for classification. And we chose the Adam optimizer to update the model's weights. The model was trained for 3 epochs, and during training we collected loss and accuracy to visualize the performance later. Finally, we evaluated the model on the test set to check how well it performs on unseen data. This part of the code defines the structure of the CNN. The convolution layer block includes con2D, ReLU, max pool 2D layer. This block detects important visual patterns in the image. The fully connected block takes all extracted features and tries to map them to the correct digit. The forward function is very important. It defines how data flows through the network step by step. Input image, convolution layer, pooling, flatten, fully connected layers, and output prediction. This code is the brain of the entire project. Here the model learns. During each epoch, the model reads a batch of images, predicts their labels, calculates how wrong the predictions are, adjusts its weight during backpropagation, improves accuracy little by little. We track both the running loss and the accuracy of the model for every epoch. This helps us understand how quickly and how well the model is learning. This part of the code is used to display predictions visually. We take a small batch of images from the test and pass them through the trained model. Then we plot some of those images along with the model's predicted labels. This is a great way to visualize how well the CNN performs and whether it's actually recognizing digits correctly or not. Here's the training loss graph. Loss tells us how much error the model is making. During training, we want this value to decrease. In this graph, you can see a nice downward slope. This means the model is learning correctly, becoming more accurate, and its predictions are getting closer to the actual digits. This graph shows how the model's accuracy improves each epoch. Accuracy measures how many predictions are correct out of the total. With every epoch, the accuracy steadily increases, finally reaching around 98% to 99%. This shows that the CNN is not just reducing loss, it is also becoming incredibly good at identifying handwritten digits. Here are some real predictions made by the model. You can see the handwritten digits images along with the number predicted by the CNN. Most predictions are correct, which visually confirms the strong performance of the model. This is where we truly see the power of the CNN. It can correctly recognize different handwriting styles with very high accuracy. After training, the model is tested on 10,000 images it has never seen before. The test accuracy achieved is around 98 to 99%, which is an excellent result. This proves that the model didn't just memorize the training data, it learned general patterns that apply to new images too. This level of accuracy is comparable to many professional MNIST models. Finally, let's talk about some challenges faced during the project. Setting up the environment correctly, making sure PyTorch works with the correct Python version, and installing libraries like matplotlib can sometimes cause issues. Understanding how convolution, pooling, and activation layers work together is also a key learning outcome. These challenges help build a deeper understanding of deep learning, debugging, and model design. Overall, this project was a great combination of theory and hands-on coding, resulting in a strong performing digit recognition model. Thank you.